Our next talk is Manuel that's going to talk about a Pristine-Union view on the Sagittarius stream. Please take it away.
Thank you very much. I wanted to say that you may have seen already some highlights of this work that I'm going to present yesterday in Guillaume's short talk, and I'm going to give you a bit more details now. And so I would like to maybe start just with this background image that I show here, because that's really much showing a bit what I'm going to present, or what is kind of the topic of my work here. I hope I can maybe convince you first that a huge part of what you see in this previous image is actually the Sagittarius stream. So the Sagittarius stream is a stream of stars that is basically produced by the tidal stripping of the Sagittarius dwarf galaxy as it orbits the Milky Way, and due to the gravitational action, as you can see in this diagram here, or like the sketch, that it leaves behind a spectacular stream of stars which really covers a significant part of the halo, and even then having different arms, like a leading arm and also a trailing arm, while we have here then the Milky Way disk and so forth. And so now going back to this image that I have just shown, this is actually a view of the Milky Way halo when we use variable Arillary stars. Arillary stars are really excellent stellar tracers to map the halo of the Milky Way really to large distances. And of course, now in this image, what you see here actually is so the different dots here are colored based on how likely these Arillary stars are part of the Sagittarius stream. And so white basically means very likely part of the Sagittarius stream. And then the other colors like brownish or bluish means like they're probably not part of the Sagittarius stream. And actually looking at this kind of view, we can pick out a lot of the features of the Sagittarius stream that we just saw. So there's one, we can actually see here the epicenter of the leading arm of the Sagittarius stream. And then also at larger distance here than the epicenter of the trailing arm. And although I didn't illustrate here like what kind of distance we're talking about, but really the Sagittarius stream covers really a significant part of the halo, really in terms of distance as well. And if you maybe now pay attention also to kind of these kind of dots here, which are kind of beyond the epicenter of the leading arm, this is actually one of the features of this Sagittarius stream that is really currently known as one of the most distant extension. And this is a spore feature, which is a distance of about 140 kiloparsec. And as you can see, this has been mapped already with Arillary stars. But of course, if we want to also get then, for instance, kinematic constraint on really this distance part of the Sagittarius stream, which might be also interesting to constrain current Sagittarius stream models, but also the galactic gravitational potential at these distances, we really need also kinematics. And Arillary stars, while they're good spatial tracers of the halo, they don't serve that well as kinematic tracers just due to their variable nature. However, there's another type of star that we can use that has similar brightness as Arillary stars, which are blue horizontal brand stars. And so on the right, I'm just showing a color magnitude diagram of the example globular cluster. And blue horizontal brand star in this color magnitude diagram actually are located at similar brightness as Arillary star, but just slightly bluer. And so blue horizontal brand stars, they are like hot A-type stars, so have quite temperatures from 8,000 to 10,000 Kelvin. And as you can also see in this color magnitude diagram, they kind of really have quite narrow range of luminosities, or magnitudes, which kind of serves them quite well, that we can calibrate them also quite well as standard candles to then map out the halo. And then the question is, of course, like, how do we identify these blue horizontal brand stars in the halo, or how do we find them? And as you maybe now see here, also in this color magnitude diagram, while we could potentially use broadband photometry, has here the issue is if we would rely on just broadband photometry, maybe the problem is often when we just use optical photometry that there's a lot of contamination of other types of star. And as you can see also in this color magnitude diagram, we have at similar colors like for instance, blue straggler stars, which are main sequence-like stars, but they are actually more compact than blue horizontal brand stars. So that means, for instance, if we would get spectroscopy, we could then look into the surface gravity, and then we could then be able to separate, for instance, blue horizontal brand star from blue straggler stars, because blue horizontal brand stars have typically lower surface gravities than blue straggler stars. So one of the methods we could use is spectroscopy to identify blue horizontal brand star. But the problem is, as I highlighted, we really want to go very far out into the halo at distance of 100 kiloparsec or even further. And so getting spectroscopy this large distance is quite difficult, especially in the era of large spectroscopic surveys, because usually these distances are still beyond the limits of these spectroscopic surveys. And so we really rely often still on methods that rely on broadband photometry or also narrowband photometry. And so there has been quite a number of works already in the past trying to see if we can use also broadband and narrowband photometry to identify blue horizontal brand stars. And I just would like to highlight here one. So there also has been a work within the Pristine survey, and I'm just referencing back also Nicolas Martin's talk on Monday about the Pristine survey, where we can actually use a combination of the narrowband photometry in calcium HK in combination with broadband photometry like SDSS then to identify blue horizontal brand stars. And there it's also really these near ultraviolet photometry might be useful, because there we have this Balmer break. And then, of course, I would like to now skip basically forward. And so there has been a collaboration of people in the Pristine survey and also in the Unions survey to try to identify blue horizontal brands really in this distant part of the Sagittarius stream here. And so there are, within this work that we have submitted to an ANA, and it's also an archive, we had a spectroscopic low BLT Force 2 pilot program where we targeted 25 blue horizontal brand star, this really distant part of the Sagittarius stream, to get to, for the first time, kinematic constraints. And so we have been analyzing these 25 or these low resolution optical spectra to get effective temperatures, surface gravities, and also velocities for these stars. And we found, luckily, that out of the 25 target stars that we had, 20 are actually really blue horizontal brand stars based on our spectroscopic classification, based on the surface gravity and temperature that we get. And so then we could really use these 20 blue horizontal brand stars to really take a look at the kinematics of these stars in this region. So I would like to now zoom in really in this part of the Sagittarius stream and take a look what we actually know in terms of like how the kinematics behaves. And I would like to maybe start now first by taking a look at some models. And so on the right, I'm showing here the velocity structure of really this distant part of the Sagittarius stream. So that means just velocity versus heliocentric distance. And so we have kind of two prominent features over here. So there's on one hand this the turnaround of the stars around the epicenter. And then at larger distance, there's the spore feature, which has a linear trend in velocity. And this is kind of one model that I show here of the Sagittarius stream. And there are also more models that also have different ingredients, what they assume, for instance, for the mass of the Milky Way. But also often they take into account the LMC. And there's, for instance, a more recent model that I show now here of the Sagittarius stream. And as you can see, they have significantly different predictions, also both in terms of the spore feature, but also of the epicenter here in terms of what kind of distance they assume. And so really by providing constraints on this part of the Sagittarius, we can really try to also constrain a bit models and also a bit the galactic gravitational potential, which is also one of the ingredients that these models have. And now I really would like to now put in also for the very first time these constraints that we can give with these horizontal brand stars. As you can see, we also kind of reproduce these two trends. So some of the stars are part of the epicenter, And then at larger distance, there's also a slight linear trend and with increasing distance where some of part of this spur feature. And we also see at least a bit more agreement with this more recent model by Eugene Vasilev and et al. So this is the orange points here. And but there's still one significant issue that we kind of realize, because if you focus here, we can see here that there's some discrepancy in terms of the position of the epicenter that our BHP star have, and also the models. And one parameter that is really sensitive on the position of the epicenter is actually the enclosed mass of the Milky Way. So in this work, we also have been trying a bit to see, okay, what do we have to change in the galactic gravitational potential such that we could maybe explain this discrepancy. And so that's why we have been then kind of trying to compare and shifting these models to basically to kind of match our data, and then trying to see how we can explain the shift also by a change in the galactic gravitational potential. And our tentative analysis shows that by kind of slightly lowering the enclosed mass of the Milky Way at these distances, which is roughly 100 kpc, to 5.3 times 10 to 11 solar masses instead of the 5.6 times 10 to 11 solar masses that this model assumes, we can better explain also this discrepancy. And then this model kind of shifts a bit then upwards to our data constraints. It is kind of nice really to demonstrate, but of course, if you really want to model this a bit more properly, you have to rerun these models or these simulations. And this is kind of just a really kind of giving a bit more quantitative statement on this. And one other aim that we had in this work as well, trying to see how we can also constrain a bit whether the Milky Way globular cluster NGC 2419 is associated to the Sagittarius tree. And so this is shown here with this white circle here, and also kind of follows the structure that we see here. So we kind of also support previous research in linking this globular cluster NGC 2419 to really this distant part of the Sagittarius stream. And so, yeah, I'm already seeing that I'm slowly running out of time here. So I think I will just then leave you with the summary slide. And yeah, would like to thank you for your attention, and I'm happy to take any more questions. Yeah, thank you.
Thanks, Manuel. A question in the audience or online? Maybe I'll take one then. So you mentioned that these are the spur feature you are seeing in the Sagittarius stream. Can you see a bit where the Sagittarius stream part, like not the spur part in this area, so the one that are much slightly closer, where those stars are in this picture? Is it closer to the orange model or the gray model? Or is it similar to the blue points here?
I
you know
guess...
what I'm saying? If you go back to your first opening slides, I guess. Yeah, so I'm talking about the stars, yeah, close to those spur feature, but slightly closer at the same kind of RE range. What are those stars compared? Like, is the kinematic different between those two populations?
So I guess, yeah, that's probably these stars then over here, because they are kind of at the distance of the epicenter. And yeah, you can see, of course, there's also some like differences here, because yeah, there's a bit like this gap here, which between at least these two models that I show here, and the epicenter of the trailing arm. Yeah, and then at larger distance we have then this spore feature. So you also see then a bit more agreement, at least with this more recent model by Eugene Vasilev. So I'm not sure if this answers your question or.
Yeah, I think that's clear. Thank you.
Yeah.
It's not the spur part doesn't meet with the model, but the actually stream part doesn't match with either of the model or sit in between the two models. Okay, thank you. Any other question for Manuel? Oh, yes. Just a second.
Very, very nice work. I apologize if I missed it, but I'm just curious, what is the mass of the Milky Way that works with the data?
Yes, so I actually put this here. Sorry if that was a bit quick at the end. So, of course, what we find here is that by slightly kind of lowering the enclosed mass at 100 kpc to 5.3 times 10 to 11, instead of versus the one that the model assumes, like 5.6, we kind of get better agreement now. So basically, I can maybe also quickly move to a backup slide. So this kind of illustrates this rescaling then basically, that you can then see that then this model kind of better matches the data here as well. And so it's not really a big difference. It's kind of just 10% or not even, or 5%. And you also can see, like, within the uncertainties, technically, it still agrees with the previous estimates from the model. So, but at least our idea was a bit for this paper to at least give an idea of what maybe the models have to change to better explain our data. But of course, I should highlight here really that if you really want to do that properly, you have to rerun the simulations, because we also make some assumptions here, and so yeah.
Very interesting. Thank you.
Thank you.
Okay, let's thank our speaker again.